We get to talk about glacier movement today. So how does that tricky little agent, get himself going? Yes.
In my glacial class this morning, he said that he doesn't. I wasn't sure if he was saying he doesn't use the terms temperate and polar anymore, or just glaciology in general doesn't use those terms. And I was wondering if you knew more about that.
I mean, just figures that he'd come along and just contradict me. Because he knows more than I do, but, at least about that. I suppose, and I don't know exactly why they don't. So it may just be that in general, let me just say in general, categories are problematic because not everything fits into categories. So that, beyond that, couldn't really say much. I think it is probably still useful to think in terms of glaciers in which the ice is near the pressure melting point and glaciers where it's not. So probably just leave it at that. So I want to talk then about deformation, movement, and specifically we're going to talk in some detail, at least, about two different major mechanisms. One simply being, one being deformation, and so in that case, we're going to have to talk a bit about rheology, which is something I defined for you on the very first day of class. Describes the strain or the strain rate as a function of applied stress. So if the ice is deforming under stress, that's why we need to talk about rheology, to see what we know about that. And the second major mechanism is sliding. And part of the upshot there is that when we have melting, that leads to lower friction. Or effectively lower friction. So we'll talk about how that works. In terms of what you were just talking about, is there a distinction between temperate and polar glaciers? I don't know, but in order to slide, we need melt, and deformation is assisted by being closer to the pressure melting point as well. Okay. So, that said, let's deal with the deformation first. And I want to specifically address deformation in a way that should, your labs next week are having to deal with glacial deformation. You'll use sort of a trick of glacial deformation, a trick of the rheology, or a trick that results from, let me just get to it. All right. One of the ways of thinking of the deformation is, we'll talk in terms of ooze and no ooze. And it's a simple dichotomy. We're not, and because it's simple, it's useful. It's not always exactly accurate, right? We're not talking often about literally does it not ooze at all, but it's still a useful kind of way to think of it, I think. let us then talk about first, I mentioned rheology. Rheology is defined as, in our case, it's the relationship between, for a fluid, it's the relationship between strain rate and applied stress. So we need to first talk about that stress. So let's start with some ice on a slab, or a slab of ice on some plane. We can consider what happens, say, at some arbitrary location within the ice. If our total ice thickness is this, I'll give that a capital letter H. If our height above the bed is just Z, and we have, oh no, sorry, I didn't mean to do it all the way like that, sorry. Again, we've got total ice thickness. We want to consider what's going on at this arbitrary location within the ice, and that arbitrary location is at height Z above the bed. And therefore, the thickness of ice above, or the thickness of this slab above that arbitrary point, is just the total thickness minus Z. We've got ice with its density. And generally always use the Greek letter lowercase rho for density, and then we'll give it a sub I for ice. And we might want to, probably useful to think in terms of, okay, I've got ice going in both directions, upslope and downslope, but I'm just dealing with a bit of it here that has a length horizontally dx. It's got, say, some width into the board here, dy. So, we've got some volume of ice. It's more than one dimension, one, 2 dimensions. It's got 3 dimensions. It's got personality and so on. So, okay. What are our forces here? Well, we've got gravity. Got the gravitational field, and say if we think about right here, we know that gravity points straight down towards the center of the Earth. Now, force is mass. Force of gravity is force of gravity is mass times the gravitational acceleration. And so, typically capital F and M, and typically using this G for gravitational acceleration. Now, that's not a stress, though. The stress is a force per area. So in this case, our area would be approximately dx times dy. So that's going to be F over dx dy. Okay, what's my mass? So my mass is going to be density times volume. course, you gotta keep the gravity. So this, of course, was the rho I. What's my volume? Well, it's that basal area, dx times dy. And again, if we're just talking about this slab here, then we got to multiply by the thickness, big H minus z. Okay. So, all right. Means our total stress is going to be density times volume times gravity divided by area. So let's just write that all out. See, I hope you see that, as I see, that I've got dx and dy in both the numerator and the denominator, so I can cancel those out. And I'm left with just the density, the thickness of the slab, and gravitational acceleration. Now, not done though, because that's pointing towards the center of the Earth, which is not necessarily what I want to know. I want to know, for example, I want to break this up into two components. I want to, first of all, know what's the component of the stress that's tending to pull it downhill, parallel to the bed. So that would be that component right there. That's going to be my shear stress. And I also want to know the component that is normal to the bed, which is my normal stress. Typically use a Greek-letter sigma for normal stress. Here's my shear stress. And we typically use a Greek-letter tau for shear stress. Yes? Sort of, yeah. But that's what you're getting at is that's our reality. That's our rheological law if we have a fluid. Let me get to that though. So my normal stress okay, how do I decompose this? I've got what I didn't put on here. Let's say that this slab is sitting at an angle theta. So I need a little trig. It's a little bit counterintuitive which trig goes to, which trig function goes to what. Let me write it. Let me draw it real quick for you. It's something like this. If I have a y and an x axis, and I've got some vector of length r, and this angle theta, then the x component is r times cosine theta. The y component is r sine theta. So let's see if we can figure out where this angle goes relative to this. If my axes are normal to the bed and parallel to the bed, then my angle theta is right here. So angle theta there, also angle theta there. So my normal component then is going to be my total stress times the cosine. So rho I h minus z g being cosine theta. My shear stress is just the same business here, but with the sign. Now we're largely, at least at this point, not going to worry so much about the normal stress. That is, well, we're just not going to worry about that for right now because we want to deal with the shear stress. We want to talk about a shear strain rate versus a shear stress. And that's where the resistance between the layers comes in, right? So, first of all, when I say shear strain rate, what am I talking about? Well, so this is going to describe our deformation parallel to this plane. Now, let me zoom in on that a bit. If I've got ice up here and I've got ice below, okay, here's my angle, theta. I'm talking deformation here. I'm supposing that the ice is deforming. If it's deforming, then if I look over some increment of vertical distance delta z, and I look at the ice velocity at, if this is z, if I look at z minus delta z over 2 compared to the velocity at z plus delta z over 2, then in general, if the ice is deforming, those velocities are going to be different. And presumably there's going to be some resistance, so I can sort of, maybe it helps me at least, might help you to visualize it as having these little layers of ice sliding past one another, but there's resistance to that sliding, like you were saying, internal friction. What's that internal friction? So in terms of the shear strain rate, that's going to be, just write it as the limit as delta z goes to 0 of this difference, difference between this and this velocity divided by the difference in elevation. And so that's just the derivative of velocity with respect to elevation. And that's what we define as our shear strain rate. Now, we could have different sorts of rheologies. A linear rheology would say linear rheology would imply a linear relationship between shear strain rate and shear stress. And let me just be clear that we are treating our ice as a fluid. So for a linear fluid, my du dz is equal to some constant times my shear stress. And that constant we represent as a 1 over mu. So that is my version of the lowercase Greek letter mu. And that's the viscosity. So the viscosity is the fluid property that describes the resistance for layers to slide past one another. Yes?
Is the one next to the 1 over mu? Is that?
Tau.
Tau.
Is that a lousy tau? Let me try again. Is that a better tau? Okay. All right. Now, that's nice, but ice isn't like that. Ice has such a pretty picture, but I guess let's go. It's not all that pretty. Ice has a nonlinear rheology. And specifically, it's described by Len's flow law. Len's flow law says that ice rheology is described by a nonlinear relationship between strain rate and stress. We use some capital letter A for the constant, and we raise shear stress to some power n, where n is greater than 1. Typical values of n are, say, 3, maybe 4, but we'll use 3 just because that's a value to use. Let's look again at what that means. We could rewrite this rheology relationship as A times tau to the n minus 1 times tau, which says that our effective viscosity is inversely related to this tau to a power. If n is 3, that means that the viscosity of the ice varies with the shear stress squared, but inversely. That means that the greater the shear stress on between my planes of ice, the lower the viscosity, and relatively dramatically lower. What did we say about shear stress? Shear stress is a function of the thickness of the slab over that layer. So that means that relatively high up in the ice, where Z approaches the total thickness H, so we have a small thickness, a small shear stress, our ice is going to be very viscous in fluid terms, practically like a solid. Gosh. And then as we get closer to the bed and the shear stress increases quite a bit, that means our viscosity, effective viscosity, goes down dramatically. So our deformation is going to occur much more near the bed than it is up high. Okay. Now, I still got this not completely erased ooze versus no ooze thing going on here. All right. This, if I wanted to graph that, and I could do that, if I, so my shear strain rate versus shear stress. for something like n equals 3, might look something like that. Right? So kind of as a nonlinear, but past squared to cubic and maybe even beyond, we sort of go along at a relatively low strain rate for applied stress and then rise dramatically and quickly. And one way to think of that is that the ice doesn't move much at all until we hit some kind of yield strength. I'll call it tau sub y. In effect, we can kind of treat ice, at least in an approximation, we can approximate the ice as a plastic material, that is, one which doesn't deform until it breaks under this yield strength. Or, yeah, the strain rate is 0 until it might deform, but the rate of strain isn't. That's not a T. Sorry. That strain rate within the material is not moving, and until I get to some yield strength, and then we get high velocity or high deformation. What is the benefit of doing that? Or okay, let's suppose that we can do that. So that du dz is 0 for tau less than or equal to tau sub y, and goes to infinity for tau greater than the yield strength tau sub y. Now, I obviously don't really mean that the shear strain rate goes to infinity. But let's think about this. If I've got ice and I'm sort of piling it up with putting more and more snow on it, what this is essentially saying is that, it doesn't move much till I reach a certain thickness on some slope. But as I pass through a certain range of thickness, it's going to start moving or deforming relatively quickly. Now, once it starts deforming quickly, it thins out again, and then slows way down again. So what that means is that the ice thickness is going to hover right around where the shear stress equals this yield strength. And that is handy for us if we want to know something about an ice profile. So, for example, in your labs, you will say, okay, I've got this glacier, but it's not there anymore. I'm on the Wind River Range. I've got these beautiful glacial valleys, but no glaciers in them. But I do have some moraines out on the valley floor. And I can reconstruct part of the former ice surface, at least under the assumption that the top of the moraine was at the ice surface, from the slope of that moraine and the height of that moraine pressed above the valley floor at those points out there. But that doesn't get me an ice surface if I want to know how much of the range was, say, covered with ice. For example, were certain low points in the ridge under ice or something like that. Well, if I say that my ice thickness is going to hover around this value where it equals the yield strength, or where the shear stress equals the yield strength, then I can just say, okay, my equilibrium condition is one in which tau equals tau y. I just erased it, but tau and now let's think about the shear stress at the base of the glacier. So given the entire thickness of the ice, that this is density times the total ice thickness now, and gravity and sine theta, and yield strength. Yield strength is going to be something that I'm going to have to infer probably from whatever part of the ice profile I can reconstruct from the moraines. Or maybe I could get it from ice that isn't gone, but has similar sorts of conditions. Rather than try to cram more down there, let's move back over here. So my equilibrium condition, rho I, total thickness h, g sine theta equal to tau y. I need to deal with sine theta because, sine is sort of an exotic function. Well, whatever. It turns out to be convenient to say, well, sine theta, let me draw an ice surface here for some kind of reference. Rock down here, ice here. I'm going to draw the slope at the surface of the ice because that's essentially the relevant slope here. And I'm going to say that my ice elevation above some arbitrary datum is a lowercase h. Okay, lowercase, not uppercase, where uppercase h I'm using for thickness. H here is going to be some height above some arbitrary datum of the ice surface. So sine theta is approximately equal to tan theta, provided I've got small enough theta. And tan theta is equal to, in this case, the way I've described it, dH dx. And I can discretize put that in a more discrete, in the discrete form of, say, a delta H or a delta X, but given that if I have some increment of delta X that I'm working with, what's my change in ice elevation? Let's plug that back in. Above. Again, now we're going to have to figure that tau y, this yield strength, is some property that I can figure out. But if that's something that I know, then I can solve now for that delta H. So if I know the ice surface elevation at some point, and I know the yield strength, and I want to know the ice elevation some distance up ice from me, well, okay, I plug that distance in here. I plug in the ice thickness implied by the ice elevation where I know it. Density, gravity, and I calculate a predicted increase in the ice surface elevation for that increment delta x. And then I step there and I go, okay, now I know the ice surface elevation here. Now I can predict what it is over here, and so on, all the way to the divide. Provided certain assumptions and approximations hold, but it's worth a try. And so that's what you will do in your labs next week. Okay. There's other interesting stuff about ice deformation, but I'm going to leave it at that because, oh my, I've got to leave enough time to talk about sliding, because sliding's pretty cool too. I mean, it's kind of cool to think about ice oozing and deforming, but wait till you get a load of sliding. There's some serious tricks involved there. Some devious ice. All right. So in this case, we're going to figure that velocity is going to be some function or vary with our shear stress over our effective normal stress. Because it's that effective normal stress that determines our friction at the base. Yeah.
So on the diagram that you had drawn, is the normal stress going down towards like the base of the ice or to like the top? But isn't the normal stress or like a release of normal force go up forward?
Yes. Technically, you're right. Technically, normal means outward from the surface. So I should have been more precise and said my reverse normal or parallel to normal stress. But it is important to remember which direction that particular stress is going. Typically, we talk about a normal force. Actually, is that outward response, say, to gravity in this case? So the reason that the ice doesn't move through the Earth is because there is that outward normal force countering the gravitational force. So we kind of simplify and shorthand a bit for purposes, and yeah, I have to put aside some of my anal retentive physics person nature to do some of this stuff. But yeah, because it is kind of, these kinds of shorthands are relatively standard, and you remind me that I forget that there are things that I'm leaving out. Okay. Okay. Now, I said, remember, stress has more than one component. It has the shear stress, the effective normal stress, or a normal. There is this normal stress, again, what I'm calling normal stress. And it determines that frictional strength at the base. The effective normal stress is going to be that due to the weight of the ice minus water pressure. Okay. Liquid H2O pressure. Okay, how do we think about this? If I've got, let me zoom in on a bed here. I've got ice up here, I've got rock down here, and in between I've got water, and let's say that by water I mean liquid. Because ice is also water. But, okay, now I've got this stress bearing down from the weight of the ice. And that is going to be communicated to some degree to the rock. But the water may have its own pressure, and that pressure is going to push equally outward on the walls of that cavity down there. And what do you know? It's going to essentially bear some of the weight of the ice. It's going to, that pressure is going to subtract from the shear stress, the normal stress, to give me an effective stress and a smaller friction, smaller amount of friction. So that's how it happens. We're not going to go through any particular. We're not going to go through trying to calculate that. But that's what is going on. We have to build up enough water pressure in there, enough liquid water pressure to make the effective friction small enough that the ice can glide. So let's say, all right, maybe you'll buy that. But what about, I mean, you know, that looks like it works if the bed is smooth, but what about when there are bumps on it? What does the ice, how does the ice happen to slide if the bed is bumpy? Well, let me just go ahead and draw a bump in there. Now, let me draw a new diagram where the water is sort of going to be now more or less invisible. If I've got a bump on my bed and, you know, ice up here, and if the bed were smooth, then it could slide, just slide. But now I put a bump in here, and now the normal surface, normal parallel component of the ice stress weight is going to be pointing like that on the different sides of the bump. So right here, that stress is going to be greater and here it's going to be smaller. Now, if say you're the ice, be the ice. If I'm under a lot of pressure, what happens to my melting point?
Lowers.
It lowers, yeah. If I'm not under so much pressure, then my melting point goes down, right? So, if I'm just at that pressure melting point up for a smooth bed, and now I've got greater stress here. Did I run out of time? Yeah. Pretty much. Okay. I'll have to finish this up next time, but the short answer is, well, if I increase the stress here, the pressure, then the water melts, and it flows around and over the bump, gets to smaller pressure over here, refreezes. Okay, but there's still another trick we have to go through because melting requires heat. Freezing releases heat. So to keep this process going, the bump's got to be small enough to conduct that heat back through the bump. So that all works for relatively small bumps, say less than 1/2 meter. And just for one last kick in the pants, I'll show you the picture that kind of proves this happens. Because, you know, you might well be like, yeah, right. That sounds pretty spiffy, but I don't believe you. And I would say, okay, well, you don't have to believe me, but how would you explain this? Here we've got a bump where a glacier used to be. We've got striations on the up ice or stoss side of the bump, and on the lee side we've got little stalactites. Because, you know, ice can't hold solute. So we get the melting on this side, we're grinding stuff into the rock, it picks up dissolved carbonates, and then down here reprecipitates those carbonates in little stalactites that point parallel to the ice motion direction.
Where is
Oh man.
It's in the book. I can't, maybe, let me see if it's on here. No, I don't have a note on that. Yeah, it's in the book. I can't remember. Yeah, I mean, it is kind of unusual. Hey, oh wait, I'm not almost. Is that right?
That's right.
Okay, so I'm not as bad as. All right, cool. So that happens for small enough bumps, which is pretty cool. That's a good trick. What about big bumps? You know, let's say now I've got a bump that's, you know, way big. Well, I don't necessarily, and here it's a relatively straightforward thing. Oh, by the way, this melting, refreezing, heat transport. This is called regelation. And that works for small bumps, say less than about half a meter in length. For big bumps, you know, say bigger than a meter, well, I don't need to, essentially if the bump is big enough, yes, I get also greater stress here and lower stress here. And if the bump is big enough and the variations in velocity required are small enough, then that extra pressure on this side will get me a lower viscosity, effective viscosity of the ice, effectively higher viscosity on this side. And I simply flow faster on this side and then slow down once I get over here. And so that's so-called enhanced creep. Love that word, that term. And that's for large bumps. You know, definitely greater than a meter. That leaves us with an in-between bump that neither trick works on. And so the medium bumps are why glaciers don't slide when they don't slide. So, but they do slide sometimes. When do they slide? Anybody know? Do glaciers slide?
When the downhill force.
Well, yeah, in general, sure.
I was curious about anything you watched.
Oh, well, we'll have to get to that. We'll try to talk about, and for glaciers, we call it pour. I've heard it called pouring, plucking. I like plucking because it's the same word we use for streams. But yeah, we're going to talk about erosion next time. And it does relate to regelation to some degree. Yeah.
You move because they're warmer at the base of the glacier as opposed to a cold base glacier that doesn't move?
Well, so here's the thing. I mean, yeah. But the problem is that most of the time, you know, there's not enough water pressure there to move it over those medium-sized bumps. It can't. Neither of these tricks work, and so the friction is great enough due to those medium-sized bumps, you know, depending on their amplitude, so that the glacier doesn't slide. So what does it do? It waits till spring. Waits till spring for water pressure. So, and then it does a little trick called cavitation. Here's a diagram. That's not a diagram of how it works. This is a diagram of how that works. So if I have it's not that hard. Okay. So up at the top I've got a schematic glacier complete with crevasses and so on, and a blue dashed line indicating water pressure. So that's where my water table would be in that porous ice. And if that water table is high enough, then I can create enough pressure down here such that the glacier will actually ramp up over the bumps. Now, of course, in order to do that, when it does that, it's going to leave cavities on the lee sides of those bumps. And those are going to fill with water. And that water has got to stay at that same high pressure. And that works for a while until it lifts up enough that those bumps get big enough and they start linking up with other bumps. And they form a continuous drainage system. And somebody pulls the cork on the whole system and all the water rushes out. Yeah. You can get a Yokolobs, but not necessarily. So here's a scenario. Say I've got a lake next to a glacier. I've got a handy way to measure the water table height in that glacier. Let me just skip. This is the Kennecott Glacier in Alaska. McCarthy is down there at the outlet of the glacier. Here's a map of it. We're going to put GPS transceivers on the glacier. We're going to put pressure transducers in this lake here and this lake here. And here's some pretty pictures of Kennecott Glacier and Root Glacier. That's a 5,000 foot ice fall. Pretty bitchin'. Okay, so what happens here? Down here we've got depth of water in these lakes. The blue is the lake up by the side of the glacier. The red is the little lake down near the crook of the glacier down there. Okay, what's going on here? This is the real sweet spot over here, because it's a complicated graph and I don't have enough time to explain it all. But what we see here, we've got water level rising in that Hidden Creek Lake. And as it does, I get greater and greater sliding velocities, horizontal speeds registered by those GPS units. But I also get uplift of those GPS units. The glacier is actually ramping up over those bumps, and you can see it. Until Hidden Creek Lake drains, and then fills up Donegal Falls Lake, DFL, fills up. I get all of a sudden especially fast uplift and sliding until it drains. I get a spike in my outflow at the base of the glacier, and the sliding tapers off and the ice settles back down and closes up those caverns. That's pretty wicked cool. And that was done by students of and the lead author of our textbook, Bob Anderson. There are some other cool graphs that you should check out. You should also check out, there's a real nice general explanation of rheologies of solids and fluids and that kind of thing. So definitely check that out too. All right, cool. Next time we will talk about glacial erosion. I'll get you your quizzes back, and you'll have a chance to ask me some probing questions about this magic here. All right, take care.